Hello. This is our second part of 3 to the electromagnetic wave lectures. This part is on the electromagnetic spectrum. So electromagnetic waves come in many different flavors or types. And what we're going to do here is go through and go over most of those or all of those types of electromagnetic waves. Now, no matter what type or name we give an electromagnetic wave, we know that it always propagates through space-time at the speed of light. So the speed isn't changing, but the wavelength and frequency will be changing depending on the type of light wave that we're talking about. And so what I've done is drawn a little bit underneath here. What we're going to have is a big rectangle like so. And we're going to have all 8 different categories on here for the different types of wavelengths, and we're going to categorize this, like I just said, by wavelength. So we'll remind ourselves that lambda is wavelength, that f is frequency, and we're going to also discuss a little bit about the amount of energy that these types of waves have in joules. And so the left side of our rectangle that we have drawn is going to represent low frequencies or small frequencies, long wavelengths, and low energy. So another way we could have said this would be small. I kind of like that better. I'm going to say small frequencies. A small frequency would be something like 1 hertz. A long wavelength would be something like 1,000 meters or 1 kilometer. And low energy might be anywhere from 10 to the negative 21 to 10 to the negative 18 maybe joules. So we're going to put 10 to the negative 21 joules there. And we'll talk about different things along the way, but in general we're representing our electromagnetic spectrum with this box here. And I'll tell you some applications to these waves as we go. Normally, books or internet sources will often draw this electromagnetic spectrum in the reverse order. So they'll put large frequencies or short wavelengths and high energies on this side, and they'll put these on the other side of the spectrum, but for our purposes this is going to work better. So anyway, we're starting on the left side of our rectangle, which represents the electromagnetic spectrum, and the electromagnetic spectrum will start with something called long waves, and usually the books or internet sources won't have long waves on them anymore, but I think it's worth mentioning a long wave. Long waves are often used in submarine communications, so if you ever find yourself on a submarine, you'll be using long waves to communicate with people. I think the next sort of wave that we're going to talk about will be radio waves. I'm sure you can think of an application for radio waves. Well, how about your car radio? Was there a time in your life that you thought that your car radio was intercepting sound waves from the radio station? Because it isn't. It's intercepting light waves. Radio waves and long waves are kind of the same sort of category of waves. Over here we could have AM, amplitude modulation, AM radio stations like AM 950. We also have FM radio stations like 88.7. FM is frequency modulation. We have an aircraft band. We have a military band, and there's several other bands that there's like a ham radio and all sorts of things. So there are lots of different frequencies or wavelengths of radio waves, and they have different purposes. In general, when you're in your car, if you set your radio to a certain radio station, what happens is it allows the resonant frequency in your antenna to oscillate at whatever radio station you plugged in. So FM, if you plug in 95.5 FM, what that really is saying is your resonant frequency for your car stereo is now 900 or 95.5 megahertz. And if you were going to tune into AM 950, 950 AM, that would be 950 kilohertz. So there's a little bit more to those numbers on your stereo than you realized. But really, all those numbers represent are the frequency of light that your antenna will allow to pick up. Okay, so leaving radio waves, we get to the next sort of wave. It's called radar, and it kind of overlaps between radio waves and the next one. Radar overlaps with what we call microwaves. So radar was come up with in the early 20th century, and when it was come up with, maybe Marconi, he tried to sell it to the American government, and the American government said, why in the heck would we ever want that? And they did not want it, talking about radar. He then sold it to the French government, who ended up using it for military purposes. The US caught wind of that and later on purchased and started using radar to track themselves and perhaps enemies. So radar started getting used after World War I believe, and into World War II. Soon after, radars began to be used in more high volume. We had to have radar antenna and microwave antenna set up all over the place, and if we have a bunch of antenna set up, we're going to have microwave antenna repairmen. So the microwave antenna repairman would go and fix microwave antenna. Well, there was one in particular who got very sick from doing this. His wife took him to the hospital, but he ended up not making it. And during the autopsy, the doctors that looked inside said that his organs were cooked. Now, this was a microwave antenna salesman, repairman, and the doctor that was doing the autopsy made a realization. If you can cook a man with these microwaves, then you could definitely cook a lean cuisine, right? And so the microwave oven was invented. Now, it wasn't called a microwave oven at first, it was called a radar range. And because radar was being used extensively for military, it was not very popular. It wasn't until they changed the name from a radar range to a microwave oven that people started purchasing them. Anyway, microwaves are another form of light. Those are about, a much shorter wavelength, about a few centimeters to 10 centimeters in wavelength. So they're getting much shorter in wavelength. Another application for microwaves, other than your ovens at home, would be your cell phones. Cell phones use microwaves. I implore you to look up the operating frequency of your cell phone and then look up the operating frequency of your microwave oven. My bet is that they're identical. Something to think about. You should look up other phenomenon with microwaves, microwave ovens, or with cell phones. It's really fun. YouTube has some good stuff. The next form of light is called infrared. Infrared light is not visible to humans, but we do sense it in other ways. Infrared light is the light that allows us to feel warmth. So an infrared light source, we might not see the light, but we would feel the warmth, or we would feel the electromagnetic waves when they interact with our bodies. So anytime you have a heat lamp in a bathroom or something, that would be emitting a lot of infrared light. Humans are an excellent light source of infrared light. We are a very warm temperature relative to other things, some other things, at 98.6 on average, and that temperature, based on that temperature, we know that humans are always giving off infrared light. There are other creatures in the world that can see infrared light. One of my favorite examples is a snake. Snakes have infrared light sensors all down their bodies. Imagine having eyes all over your body. What do you think a snake really sees? It must be out there. What comes after infrared? Well, I've already placed it in there. It's a very famous, known set of light color, and that is our visible light spectrum. And that visible light spectrum is comprised with Roy G. Biv. This is why I did my spectrum backward. If we did it the other way, it would be Vib G. Oren. Who knows that guy? But Roy G. Biv is our friend, and he represents the colors, the visible spectrum, the colors of the rainbow. The visible spectrum is approximately 700 nanometers to 400 nanometers. And so notice we've gone from light waves that are have wavelengths of 1,000 meters all the way to our visible spectrum where we're at 700 nanometers. So that's over 1 billion times smaller than long waves. So this is a wide variety of wavelengths, this first half of our spectrum. And it's important to notice how little Mother Nature actually allows us to see as humans. The next form of light is starting to get to some dangerous forms of light. Not that microwaves aren't dangerous, but these are a little bit more violent with your skin. These are UV, UVA, UVB, and UVC. Now UVA is less energetic than UVB, and UVC is the most energetic, but all of them can cause some permanent damage to your skin. I like that a lot of tanning places will make the argument that they only use this light, or maybe UVA and UVB, but no UVC, so they're safe. I don't know that any UV light is technically safe for human skin, but I guess that UVA and B would be less detrimental than UVC, because as we go down the spectrum, the light gets more energetic. Okay, so UV light comes a lot, we get a lot of UV light from our sun. You don't really feel it, but it's the light that burns you. There are a lot of other animals that can see UV light. My favorite example are many birds of prey. Birds of prey can often see UV light, and that helps them with their hunting, because mammals tend to mark their territory, so to say. Tell you what, my dogs know where they live, so when they're on a walk and they're going to the bathroom and other lawns, I know they're not marking their territory. I think they're just trying to make fun of the other dogs. But anyway, mammals tend to do this, and so when a bird is soaring overhead, if they see a few fresh puddles of pee, those puddles of pee happen to reflect UV light really well. And so those puddles will end up acting like a blinking light toward dinner for any bird of prey. Anyway, UV light has many applications. Sun tanning and birds of prey are a couple. The next form of light are called X-rays, and X-rays are getting into a very powerful or energetic light. X-rays are obviously used to look through surfaces at other surfaces. We use X-rays in the medical field quite often. X-rays do cause irreparable cellular damage when they go through you, and so it's important that you try to remember that and get as few X-rays as you can throughout your medical life, I guess. Okay, and finally, the most energetic form of light is known as gamma rays, and that's the Greek letter gamma. Gamma rays. Gamma rays are so energetic that we don't have many sources of them, or any maybe, on Earth that are not man-made. But we know that we get gamma ray bursts from deep space, and often from entities that we call quasars. But gamma rays are the most energetic form of light that we think exists. So on this side of the spectrum, we have very large frequencies. We have short wavelengths, and we have very large or large energy. Large energy might be 10 to the negative 12 joules. It doesn't sound like a lot, but for a tiny little light wave, it's quite a bit. Short wavelengths would be approximately 10 to the negative 15 meters, or a femtometer. And large frequencies would be about a gigahertz. 1 gigahertz. So that is the electromagnetic spectrum, and these are all the different flavors that light come in. And normally we would talk about an hour about this in class, and we just don't have that luxury, so this is the bare bones and some of the most important information I think you should take away from the electromagnetic spectrum. One more little note, just for funsies. We often measure these wavelengths instead of in nanometers in angstroms, so 7,000 angstroms or 4,000 angstroms, where 1 angstrom is equal to 10 to the negative 10 meter. So that's another unit that we often use when we talk about light or light waves.